Good afternoon, everybody. I will already start welcoming everybody. I see a lot of people coming in. Just to fill the emptiness, use that time a bit to say hello to everybody. We'll repeat my welcome again in a couple of seconds. We have a lot of participants. I'm very happy to have so many people interested in this in the topic of seasonal thermal energy storages. It's about 50 participants now already online. We have, and still people dropping in. We have a lot of interest in the topic, very well. Reaching almost 60 participants now, very good. We have a quite tight program. We have a lot of things to do. So I would like to now officially welcome everybody. My name is Ralf Roman Schmidt from AIT, Austrian Institute of Technology. I have the honor to be moderator of this webinar today, although I have to admit I haven't organized it specifically. So thanks very much to the good people from Youth and Power for organizing, inviting, putting all the things together, setting up the technology, the Zoom meeting and stuff. Very good. Reaching almost 70 participants. That's very good. So to everybody, I mean, we all may had a couple of webinars, but I would like to ask everybody, obviously, to mute yourself, please, for the webinar. Switch off your cameras, except the speakers. We will have panel discussion at this very end. Until this time, please, if you have any questions, there is the Q&A box in the Zoom window. It's not always called Q&A box. In German, it's called F&A box, for example, but you will find your national translation in the Zoom window where you can put in questions to the speakers. Without further ado, I would like to start then the webinar. I can go for the next slide. Exactly. So just a very quick overview of what we're doing. I will start a bit with the energy economic view on seasonal thermal energy storages. Then we will have 4 very interesting presentation on 4 ongoing EU-funded research and demonstration projects. Thunder on pit storages, uses for heat on underground storages. Treasure on pit storages, uses for heat on underground storages, thunder on thermochemical material-based storages, and interstores on reused infrastructures and cavern storages. Then at about 10 to 3, I will share a bit of insights we had in a previous discussion from the renewable heating and cooling energy technology and innovation platform. And we will end with a panel discussion on all these different technologies and the challenges and solutions and the options we see for integrating seasonal thermal energy storages. Again, if you have any questions, we are reaching now 80 participants almost. If you have any questions, please type them into the Q&A box at your Zoom window. Yeah, as said, we have 4 very interesting speakers: Wim van Helden, Sylvia Trevisan, Safer Uwe, and Abdul Rahman Dash on these 4 different projects. I will come to those people a bit late, a bit more in detail. And again, my name is Ralf Roman Schmidt from AIT. And since I do also a bit of research on seasonal and thermal energy storage, not so much on the technological detail, but I work a lot on energy economic view. And so I will give a bit of an introduction into, from my point of view, on seasonal thermal energy storages. So why do we need those storages? That is discussed for a long time. I'm in district heating for over 15 years. All the time we are discussing seasonal thermal energy storages as a key element for decarbonizing district heating networks, since they can shift excess heat in summer from whatever sources you might have to the winter, and reduce the winter demand from other sources. As you see at the bottom, this is a situation that's very typical in many district heating networks. A lot of heat sources have an excess, and not only solar. It's very often the discussion on seasonal thermal energy storages is coupled to solar thermal energy, but that is one heat source that's relevant, but there are many others, as you can see on that screen. And then obviously that storage can shift whatever is exceeding the summer heat demand to the winter. However, especially in not only in urban systems, but even in small rural systems, several 100,000 cubic meter of these storages would be required, and that's very capex intensive. So we need to really look, does it make economically sense to integrate the storages? And in order to have a bit of an idea of the economic feasibility, we did I would like to present you a very simplified assessment. We are looking at the return on investment in a storage investment. So in year 0, we are investing in a storage tank, and each year we have some savings. That is the alternative fuel cost we're going to substitute in winter times. Obviously, we have to pay maybe some heat cost in summer times, and this is operating for 50 years. And the return on investment will tell you, is your investment worthwhile after 50 years? So if the return on investment is positive, it is a good investment. If it's negative, it's a bad investment. Again, it's a very simplified assessment, analyzes there's only one cycle, charging in summer, discharging in winter, replacing some most likely fossil fuel. It's only one cycle, no operation beyond seasonal charging. In reality, you might aim for 2 or more cycles, but this, as a very simplified assessment, assumes one cycle. One thing we introduced is the delta T, so the temperature lift in the storage can exceed the normal delta T, or the normal temperature span between supply and return line. Normally, you might have 95 to 60, 95 to 50, so 30, 40, 50 degrees delta T. We are assuming that there's an option to increase that temperature lift in the storage, either using a heat pump or by using storages that can be loaded up to, for example, 150 pressurized storages, for example, that can be charged to very high temperatures. So now going a bit into the simplified assessment, we're looking at a reference case where we have some, for example, €5 cost of the heat for charging in summer. The fuel replaced in winter costs €165 per megawatt hour. Some construction cost of €175, and this temperature lift, what I was talking about in the reference case, is 60. Now, when we're looking at the worst case and the best case scenario, obviously in the in the reference case scenario, the return on investment is slightly negative. So it's in the reference case scenario with these assumptions we did, one charging cycle, the seasonal storage would be not economic after 5 years. The worst case obviously is even worse. In the best case, where we have an assumption that we have free heat for charging, the fuel replaces very expensive, €300 per megawatt hour. The construction cost is very cheap, and the temperature lift is very high. The seasonal storage would be pays itself after about 10 years. Now, I would like to look a bit into the details. Why is it happening? Looking at these different parameters. So cost of charging for heat. So again, on the left side, you have the return on investment. In the reference case, this is €5. It's in the middle. It's slightly negative, and you see it doesn't really matter if you have free heat or if the heat costs €10 or even more. There's very little impact and very little sensitivity to the excess heat cost you have in summertime. It could cost 20, it could cost €30. Your return on investment wouldn't change a lot. There's no big impact. Even if you get paid for receiving, if you have minus €10, your return on investment wouldn't have a huge impact. Now, the interesting construction cost obviously has an impact. So as cheaper you are, if you go towards €100, you have a return on investment of about 70% after 50 years. That's very good. But it's difficult to very much influence the construction cost. There are options, and I hope we will see some options in the later stage of the webinar. But that's an important parameter. very much important is this temperature lift as well. And I think that's very interesting for me. Again, in the reference case of 60 Kelvin temperature lift, it's not economic, but if you go for the 30, if you would have a return line of 60 degrees temperature, you can charge your storage up to 90, you have 30 delta T, 30 Kelvin delta T. That reduces your economic efficiency very much. However, on the other side, if you're able to boost that up to 90 or higher by, for example, reducing the return or the lower part of the storage temperatures to only to 10 degrees maybe, or boosting the upper part of the storage to 140 degrees, you're increasing your economic efficiency a lot. And then the last parameter I would like to look at is this cost of fuel replaced. Again, in the middle, it's not really efficient, but if you're above 180 euro per megawatt hour, you're coming into the economic zone. And summarizing these slides, you see if you go above 70 degrees, the temperature lift, or above 180 euros per megawatt hour, or specific construction costs below 160, you can go positive on your return on investment after 50 years. And just to give you a reference, the cost of fuel replaced, 180 euros per megawatt hour, that equals about 5.45 euros per kilogram hydrogen, if hydrogen is the reference fuel. And that's very much the order of magnitude we are discussing at the moment, hydrogen prices. Sometimes maybe 3, 4, 5, but even higher prices for hydrogen. To give you another reference, there is one hydrogen charging station in Vienna. There you can get hydrogen for 2.40 euros per 100 gram. So that's 24 euros per kilogram. Just to give you a reference, what is hydrogen value. I'm already late in time. I have a case study also, a very brief case study, just skip a few slides just to show you what we did. We were looking at now really a more detailed assessment of a case study, looking at the hourly heat demand. And you see very much in this figure, that's a optimized heat supply, optimized and decarbonized heat supply for 2040. We see a large seasonal storage has been modeled here, and you see in the summertime, there is a heat pump actually. Sorry for not translating that figure I just noticed, but this red lines are heat supply by heat pump over the year. You see in summertime, there's a very low electricity prices, high heat source temperatures, and this is possible. This makes it possible to charge the storage. And in winter, you see some discharging of the storage. So that is part of the cost optimum solution. If we say, no, you cannot integrate the seasonal summer storages, there's an optimizer behind it, an optimization-based approach. Much more, so he cannot use, obviously, all that cheap electricity in summer times. And he has to use a lot of biomass in this case in winter times. And the overall costs are 2% higher than in the case with the seasonal storage. Summarizing my first introduction, for my very initial assessment, most important factors for economic feasibility of seasonal storages are the temperature lift, specific construction cost, and the cost of fuel replaced in wintertime. Obviously, you can add revenues from short-term operation. In Austria, we see solid biofuels represent the main competitors, and they are very cheap, much below this 180 euros. Sorry. And there's a lot of uncertainties that needs to be taken into account, because if I said we are looking at the technical lifetime of such a storage of 50 years, and over all these 50 years, we were assuming stable conditions. There's a lot of uncertainties here. I will skip that slide, and then I will already introduce the next speaker in the meantime. So we will start with the Treasure project that focuses on pit storages, and that is presented now by Wim van Helden from AEE Intec, where Wim is the project manager of the Treasure project. Wim studied technical physics and has a PhD in energy technology at the Eindhoven University of Technology in the Netherlands. He is at AE-INTEC for about 10 years. So welcome, congratulations to your 10 years anniversary at AE-INTEC.
Thank you.
And he works, a lot of people know him working on compact thermal energy storage and large thermal energy storage. He is also active in the International Energy Agency. And yeah, with that introduction, the floor is yours, our presenting pleasure.
Thank you. Yes, in the next 10 minutes, you will hear more about the Treasure project that started in January this year. It's on demonstrating large pit thermal energy storages in Europe on several places. A bit about, say, the background of the project. It's a 4 years project with runtime until 2027. And it's, as said, working with pit thermal energy storages. We call it underground thermal energy storages because one of the pits is actually, say, an underground tank, therefore with vertical walls. And here you see in this picture, the schematic, the main components of a pit thermal energy storage, in which also most of the components will be worked on in the project. So the diffusers, the storage medium, which is water, an insulated cover, and then a waterproof liner to make sure that the pit water does not leak to the environment. And then, of course, the connection to the district heating grid. What the basis is for looking at pit thermal energy storages is that it's a technology that is well spread already in Denmark, connected originally to solar thermal systems, district heating systems connected to solar thermal fields. Then, of course, you need a seasonal storage in order to capture the solar heat in summer and use it in winter. We made a first calculation of what the potential of pit thermal energy storage for district heating in Europe could be, based on the total final consumption of district heating heat in the EU in 2018 of 446 terawatt hours, and a fourfold growth until 2050 that is projected. And then assuming that these heat demand, 30% has to be stored in the storage. In practice, this will very much depend on the storage or on the district heating system, and it could be lower, between 5 and 15%. But for the case now, let's assume 30%. And then 40% of the large thermal energy storages that are needed are pit thermal energy storages. So the rest will be filled in by other technologies. The present need for storage capacity then would be 54,000 gigawatt hours, and in 2050 this would be fourfold, so 220,000 gigawatt hours of storage needed. Meaning that if we start now with the first storages, the monitoring storages of PTES in Treasure in Hoje-Taastrup, which is 70,000 cubic meter, which has about, say, 13 gigawatt hours. And after the end of the project, we'll be developing the 7 demonstrators. We will have about 100 gigawatt hours. And with the satellite initiatives that are connected to our project, about 16 other demonstrators, we will come to about 423 gigawatt hours. So in order to arrive at this 2050 goal of several hundreds of terawatt hours, we need an acceleration. And this is one of the aspects that are key to the work that we are doing in the Treasure project. So what are we doing in the project to make sure that there is an accelerated uptake? We raise awareness by informing people about the technologies, about processes, permits, procedures, etc., and to actively disseminate this and to participate or to let stakeholders participate in our processes. Then the second point is to reduce uncertainties in the technology by getting more awareness on the permitting process, making sure that there is a sort of uniformity also of the procedures, and to work on standardization and key performance indicators in order to make sure that, say, decision makers and insurance companies have more grips on the calculation methods to determine what the risks are of the investment. And then, of course, another aspect is to shorten the realization time, make sure that there is a uniform communication, and that there are uniform protocols, and that we have experience exchange between the different demos in order that, say, the first 10 projects are a bit slow perhaps, but the next few thousands of projects are a bit faster. The fourth point is to decrease costs. Of course, when uncertainties are reduced and the realization time is reduced, then the costs also will be reduced. But we will also try to approach this with development of better components, development of better processes, and also to exchange experiences between the different projects. So what is it about the demonstrators? We have 7 demonstrators in 5 European countries and 2 so-called monitoring PTES systems. The monitoring PTES systems are in blue, number 1 and 2 in blue, which are in Denmark, Hoje-Tastrup, 70,000 cubic meters, and the second one in Poland, Lidzbarsk-Warmiński, of 15,000 cubic meters. We do extended monitoring on these pit thermal energy storages in order to get grips on the temperatures, mass flows, etc., depending on the operation and on the weather conditions. And we have number 1 to 7 in red, the demonstrators. Rostock in Germany, which has the biggest volume. Then in France, Pau, in the south of France. Then number 3 in Pančevo in Serbia. Then number 4 in Bytom, also in Poland. Number 5 in Vienna, in Austria. Number 6 in Krosno, the second demonstrator in Poland. And number 7 in Hechingen, the second demonstrator in Germany. These systems all have different integrations into the district heating system. And you will see now 2 demonstrators, how they will be integrated into the district heating system. First, the Krosno demonstrator in Poland. Poland has a broad program in order to switch from coal to renewables for the district heating. There are targeted demonstration programs in place. And the Krosno project has already done a first round of feasibility, and they found that there is a limited solar thermal power capacity because of constraints in the surface area available, and this is 2 megawatts. And they also subscribed into a competition to get subsidy for this demonstrator. In Poland, there are 7 rounds per year to get subsidies, and this is in a sort of contest tender. This is about the system. So to the right you see the solar collector field, and these are connected to the seasonal heat storage here in the purple area. Heat pumps are also connected to the system, then they can elevate the temperature in the storage. Then the stored heat when there is demand is pumped to the end users, which are in the city. And when no maximum temperature is reached of the storage, then the peak source will be providing extra heat to the district heating system. This is a setup for Poland, for Krosno. Then we go to Serbia. Serbia is a so-called big solar project in Pančevo. The first iteration of the feasibility study was done by Solid, the Austrian partner in our project. And the idea is that a potential analysis for solar district heating in Pančevo was done. 3 suitable system concepts were developed. Then a techno-economic variation of different sizes of collector fields and seasonal storage were done. And an evaluation was done of the land that is suitable for the system. And then the feasibility study got into more detail into the system. Here's the system schematics. So a solar collector field here on the left, connected either directly to the seasonal storage or directly to the district heating system, or to a absorption heat pump. And then a gas boiler is used to give the additional heating in peak demand. You see here some first figures on the system. What is interesting also with connection to the presentation that Ralf Roman gave is that the projected capex, so the investment costs are approximately 21 million. But this is for the storage, not included is the natural gas boiler and the equipment, the transformer station, the land, and the needed railroad underpass with the connection to the district heating system. And the operational costs are approximately €6.5 per megawatt hour per year for this system. This was to give you an idea about the variation in the demonstrators. And with respect to time, I will limit myself to these two. This is the consortium. We have 24 partners, ranging from, say, very early in the value chain, the research institutes and the engineering companies. Then we have component developers, we have material developers, and also building companies, and then also the institutes or companies that are connected to district heating and to the planning of district heating systems. With that, thank you for your attention.
Very nice. Thanks, Wim. Again, no question and answers directly. So again, question to Wim's presentations in the Q&A box. And at the end, we will have more time to talk about these questions. So now going directly to the next presentation of uses for heat from Silvia Trevisan from KTH. Silvia has a master's in energy engineering from University of Genoa and a PhD in energy technology from KTH. She's focusing on cost-efficient thermal energy storage solution, spanning quite a wide range from component development, prototyping, lab validation, alongside comprehensive technical, economic, and environmental system performance assessments. So, Silvia, looking forward for your presentation.
Well, thank you very much, Ralf Roman, for the nice introduction, and nice to meet everybody. Now we'll be giving you some more insight on this project called Uses for Heat, which actually stands for underground large-scale seasonal energy storage for decarbonized and reliable heat. So the main, let's say, objectives and also the overall goal of this project, it's basically to demonstrate some innovative and large-scale seasonal thermal energy solutions for primarily decarbonized heating in the context of district heating network, and also for with the goal, let's say, of savings in terms of waste heat and also, of course, economics. Going a bit more into the specifics, we aim to actually develop and demonstrate throughout the end of the project two specific, relatively large scale, let's say, demonstration sites up to TRL 8, so pretty much a commercial level of two different technologies when it comes to seasonal underground storage. In doing that, we are also demonstrating some key technologies for that, and I will go a little bit more into the details. And together with that also, basically an energy management system coupled with some sort of predictive operation and maintenance. So basically a system that can enable us to have a better management of the grid itself, the coupling with the storage itself, and also informing us on any needs for maintenance upfront of events, let's say. In all of that, of course, we also try to have a broader perspective on the potential of these projects and to perform some kind of comprehensive assessment looking into environmental impact, social impact, as well as financial impact of the specific demonstration site, but also on different replications and possibilities for those. And of course, we want to promote the project as a whole and in general the integration of seasonal energy storage in the district heating network, I would say, as we are doing right now. Just to give you some flavors of it, here you see some of the numbers of the project. So we are 27 partners, similar to the project before. We do span pretty much across the whole sector, let's say, from research institutes to more technologies and material developers, as well as some of large district heating network operators in that. There are, let's say, 8 different countries involving, I would say, at least 5 district heating networks operators in the consortium itself. And we have a total budget of about 12.5 million euros, of which 10 of them are funded directly from the European Union itself. Yeah, giving you some more specific on the 2 demonstration sites we have. So one, it's located in Riva del Garda, which is in Italy, in the north part of it, close to the big lake of Garda. And the other one, it's in Oslo. So in Riva del Garda, we're going to demonstrate aquifer thermal energy storage, which is actually going to be coupled with 2 additional technologies, primarily ground source heat pumps, which basically will provide a boost in the temperature to properly couple the ATES solution with the district heating network, and also some thermophotovoltaic panel, which beside providing some green power for running the heat pump or running any other auxiliaries, will also provide some preheating of the water itself. And important to say that today, basically, the Riva del Garda city has already its own district heating network, which is primarily fed in by a paper mill, which provides some constant heat basically throughout the year, but the vast majority of that gets wasted during the summer period. And that's the type of heat that we want to store, basically. Something similar happens in Oslo. In there, it's a much larger district heating network, as you can imagine. And today, the district heating network, it's primarily fed in by waste combustion unit, CHP, basically for that. And of course, there is first incentive in actually reducing the amount of waste heat burn, but also they do have today basically waste heat throughout the summer that they don't actually use for district heating network. And then during the winter, instead, in the peak period, January, February, and so on, they need to start oil-based boiler. So having basically a pretty strong impact from an environmental perspective. And that the goal is to install a borehole-based thermal energy storage in a new quarter, basically, of the city itself. The borehole storage will store the waste heat produced during the summer, but it will also be coupled with some concentrating solar power units, which will provide basically an additional heat source. And the goal is also to understand how this could be replicated in the case of a lowering of the waste production and reduction of the base load also during the summer itself. Yeah, I was speaking about some key technology development during the project itself, beside the storages. So there are some specific goals in here, which deals with the development of some specific drilling equipment, both the head of the drilling machine, which will be used for the ATES solution, but could also be used for borehole installations. Some innovative pipes, primarily for borehole storage, able to work both at high pressure and also high temperature, up to 95 degrees. A groundwater heat pump itself connected to the ATES system as well as to the district heating network. Some advanced hybrid photovoltaic thermal panels, so basically able to, at a higher efficiency, provide both the power, electric power and thermal ones. And then the integration of concentrating solar thermal collectors with underground storage units, which are not pit storages, which, as Wim was saying, it's something rather commercial in a way, together with the management system that I was mentioning before. Well, I mentioned that we are going to have these two large-scale demonstration, but of course the scope of the project is also broader, and to understand the impact of this in different contexts. So we have these 4 replication sites that you see there. Kozani is a city in Greece, as well as Zagreb, while in Croatia. Both cities have relatively large-scale district heating networks, and in there the goal is basically to understand in the context of the local decarbonisation plans that they have already, to understand how seasonal thermal energy storage could be integrated and how, in general, the technology developed throughout the project could play a role into that context. And then we have other 2 sites which are a bit different. In Kvarnholmen, it's a district here in Stockholm, and there they do have already a cavern thermal energy storage, or I would say maybe just a cavern. And the goal is to understand, considering a completely different technology from a seasonal thermal energy storage perspective, how that could be integrated into the context of the local district heating network and how to best exploit it. While Aquatonic, it's a fish farm in Bulgaria, and there the goal is to understand on a much more or much smaller, let's say, environment, so just the industrial site itself, how a large amount of waste heat throughout the summer could be actually exploited afterwards, primarily for the factory itself, heating and building heating in the site there through some seasonal storage itself at a much smaller scale. Yeah, and just to give you a little bit of a summary, I would say, and keeping the time short, this gives you a bit of an overview of where we at when it comes to the overall projects and the plan activities. So the project, as I mentioned in the beginning, it's going to last 4 years, and it started basically in the beginning of this year. So right now we are in the process of finalizing the main engineering for the demo sites themselves, which then will start the main installation of the units. And we plan to have a demo, the campaign, let's say, in the different demonstration sites, which will start throughout the last year of the project, and then of course will last actually longer than that. Well, throughout the rest of the project and the full duration of it, we have some activities in terms of techno-economic and as well as environmental and social comprehensive assessment of the demonstration, as well as the replication, together with some general dissemination and communication activities. I wanted to highlight some of the challenges and the opportunities that we see in the project, in the context of this project, which I think are relevant, maybe also as an idea for later on discussions. But we see quite a raising engagement and interest in general from local communities, district heating network operators, and so on. They do see the impact of these technologies, which I think it's great moving forward. At the same time, on the bad side of this, we do see also a strong lack of regulations, and particularly not really common approaches throughout Europe, which can strongly hinder, I think, the development of these applications. As well as, of course, quite of an intensive capital investment that's needed from the beginning, which leads to longer term, which might be very tricky at this stage when technologies are relatively new to the market. But at the same time, we do see a very large opportunity when it comes to sector coupling and the rising need of flexibility, which I believe this type of storage is combined also with other type of storages, much shorter duration ones in the network itself, can actually support the overall system. And yeah, I think that's my last slide. And thank you.
Wonderful. Thanks, Silvia, for your presentation. There are already a couple of questions in the chat. So if you have your question, or if you're interested in the questions from the others, not the chat, sorry, the Q&A box, check the Q&A box and put your questions inside. Now going to the third presentation, Sander Safer-Ure from PCM will present the project. He's a mechanical engineer with over 4 decades of experience. He worked as a building service consultant. He is a former chairman of the CIBSE Thermal Storage Group in the UK. And he's also founder and managing director of PCM Products, a company specialized in phase change materials. And now he's presenting thermochemical storages in the Sander project. Safer, floor is all yours.
Okay. Thanks, Rolf. You made me old now, 40 years. Let's start. How do we boot this thing? Okay. If you bear me a minute. Yeah. The Thunder basically is what it stands for is that based on is taking the waste heat from data centers and boosting up and in the form of thermochemical energy storage and utilize all the district applications. And we have various partners. I won't go into details, but across to Europe and all specialize in their own areas to create that environment whereby we can generate enough heat to serve the surrounding areas. And how we do it is the data centers. And the principle of cooling means really, rather than putting the cooling into the building, we extract the heat and dump it somewhere. Most of that somewhere tends to be either air or sometimes you can use other places. But at the moment, this is the conventional technology. We extract the heat, dump into air via chillers, cooling towers, or any other mechanical cooling means. And what we are trying to do, use this low grade, 25 to 30, 40 degrees C heat. And first of all, as part of that Thunder project, develop a cost-effective heat pump so we can take that low grade, bump it up all the way to the 120 degrees C level, 120, which it makes it a useful heat for us. But nevertheless, second option, if you like, developments, we need to store that heat to optimize the peak and the low, if you like, the consumption period and level the loads. And once we achieve the high grade temperature, if you like, the heat pump on the stage one of these first developments, and taking that low grade to 120 levels, we have two options to distribute. One, either going to the static, like a district cooling system, feeding in and circulating throughout all the way up to the 120 degrees here to serve various industries. The main challenge with the district heating is the cost. It requires a significant investment as well as a disruption to the whole existing city structure, digging up everywhere. So sometimes if it's not practical, the second option on the left-hand side, the mobile. So we can put that heat, boost it up, put in a tanker and transport via either rail or road into where the basically usage is. And really, as we've said, our Italian partner, HiRef, is specialized on refrigeration technologies and heat pumps. So what we need to do really to develop this low cost and environmentally friendly as best as we can, a mechanical heat pump system, so we can take that 30, 40 degrees C water, bump it up to the 120. The current heat pumps at the moment is capable of up to 70, but conventionally propanes probably can go a little bit higher, but no more than 75, 80. There are CO2 heat pumps, goes high temperature, but they are very expensive, very costly. So therefore we try to develop some cost-effective, practical HFO-based refrigerant heat pump systems to give us 120 degrees C. I'll explain you later why we need that high heat beyond the useful heat temperature, and because also we want to store this in thermochemical. Those of you who are not familiar with the thermochemical is if you cast your memory back in your university days is exothermic reaction. So if you introduce water into certain salts, they react and they generate heat. And that's what it is, the thermochemical. But in order to use the salts in a meaningful purpose, you need a surface. Surface area, something to absorb. Most common one is the vermiculite or any other material absorb that salt. And when we introduce the moisture, it reacts, it generates heat. But nevertheless, once you generate the heat, it's saturated. You need to put excessive heat to be able to dry and take the water out so you can reuse it. And one of the reasons we need that 120, unless we get to that sort of high level temperatures, we will never be able to dry out the thermochemical material. So if you don't dry out, you don't get any heat out of it in the next round. So to make it a long term, we need both high temperature heat pump to boost it up, as well as a reliable thermochemical material. At the moment, there are so many thermochemical materials you can use, but unfortunately, all of them requires a very high temperature heat, 200 degrees C and above. So anything less than that, less than boiling temperature of 100 degrees C is the challenge. And there are quite a number of options, but hydration and dehydration is the biggest problem for low temperature thermochemical materials. So really the Thunder, we are trying to overcome those high temperature heat pump, cost effective and practical, as well as come up with a practical thermochemical thermal storage, so we can store as much as we can while the energy is available, bridge the gap when the energy is required, and deliver either district heating fixed pipework systems or using the tankers. And that really is the real essence of the theoretical study will be applied in practice in Bulgaria. And there is an existing data center, and the heat at the moment is being wasted. So the idea is capture that waste heat, boost it up with heat pumps, store in the thermochemical energy storage systems, either in a static and distribute to nearby villages that heat, or alternatively explore a longer distance using the tanker options. So that is the essence of the Thunder projects, to prove this concept is practical and applicable. And of course, it justifies economically, the most important thing. And that is the principle of the concept of what we are aiming using an existing data center. We know the performance of the data center, record the data, and try to use heat pumps and the thermal energy storage system to utilize that waste heat as best as we can, and look in the practicality, life cycle, as well as the economics of this as part of the Thunder project. And that theory, basically, the mobile has been applied in principle. On the left-hand side, you can see in Germany, they developed this, basically, the tanker, the yellow one on the left-hand side, is a thermochemical tanker. But the problem is, of course, you can see the site is an industrial site in a very high temperature heat. Unfortunately, we don't have that in the data center. So we need to come up with a new thermochemical material. We can charge and discharge around 70, 80 degrees Celsius levels. That's the challenge for us. But on the other side, also the practicality of this transporting heat is already been applied. And on the right-hand side, you see the phase change material tankers. And they are sodium acetate based simple tankers. But the difference between the thermochemical and the PCM specific gravity is more than 1.5 of the water. So therefore, it is a very heavy, and therefore it's a very limited amount of energy you can transport before exceeding the road weight limits. On the other hand, thermochemicals, vermiculite is those of you who are not familiar with this terminology, vermiculite is a cat litter. And if you have a cats, they use for toilet, and that sort of light material, and is going dry, and therefore you could transfer significant amount of energy without the weight limits. So that's the benefits of probably what we are trying to explore. And I hope I managed to give you the flavor of the Thunder projects. And although basically I put this, but question and answer probably will come at the end of the day. That's my presentation. Thanks, Rob.
Perfect, Safa. Thanks for your presentation.
Stop sharing.
Yeah,
Yep.
Wonderful. So we should see again the screen from Unit Power. Yeah, it switched for me. It switched automatically to the next presentation. I will just go directly to the Interstores project, presented by my colleague actually, Abdul Rahman Tahaj. He's a scientist at AIT. He's in different groups than I am, but we work very close together in various topics. Abdul studied mechanical engineering and has a PhD from the University of Innsbruck in planning and construction of seasonal thermal energy storages. He's active in various national and international research projects. He works with storages, heat pumps, district heating, heat and moisture transfer in insulation materials, both on simulation and experimental domains. And again, he will now present the Interstores project. Abdul, the floor is yours.
Yeah, thanks, Ralph, for the introduction. So, ladies and gentlemen, good afternoon from my side as well. So, my plan today is to walk you through in a journey through some innovative solutions for seasonal thermal energy storage applications within Interstores project. But before that, let me briefly introduce Interstores project. So Interstores stands for the International Innovation Network for the development of cost and environmentally efficient seasonal thermal energy storage. And it's a sister project to both uses for heat and the treasure. So it is within the same call, and it has a funding or a budget slightly over 11 million euros thanks to our associated partners. So Interstores basically is coordinated by MLU, Martin Luther University, Halle Wittenberg, and it brings around 14 partners together to collaborate all together and invest all this budget for a sustainable future in order to put their efforts for 2 demo sites here in the European Union. This project has started by the beginning of 2024, and it's going to last till the end of 2027 if everything goes smooth, hopefully. And the main objective of Interstores actually is to focus on the 5th generation of seasonal thermal energy storage. So our goal within Interstores and this 5th generation is to take and to push forward as well the know-how and the knowledge beyond the conventional types of seasonal thermal energy storage. And that's why one of the pillars within Interstores would be the repurposing of legacy infrastructure by reusing the existing abandoned or unused infrastructure as seasonal thermal energy storage. Simultaneously, since we are looking for some abandoned areas or abandoned infrastructure, it might happen that those abandoned infrastructure, they come with multiple units. So here we would like also to invest some time into understanding the combination of heat and cold storage with different temperature ranges as well. Then after that, we would like to put some efforts as well to the self-healing materials or the sealing for the seasonal thermal energy storage that have an improved LCA and a very good environmental footprint, and simultaneously to focus more on innovative solutions for insulating seasonal thermal energy storage applications. Now, that has been said, let's move on to the 2 demo sites that we have within Interstores project. And here I'm going to list down also all the innovations and technological innovations that we will have with each demo site. So our first demo site, it is in Germany with a total volume of 18,000 cubic meter. As you see it on the left-hand side of the slide, this is located at the city of Ingolstadt in campus, and we call it Reno Estes. So reutilization of infrastructure as a seasonal thermal energy storage. Then our second demo site, and also we are proud of that demo site, it is Varanto Vectis, that is located in Finland with a total volume of 1 million cubic meter, making it the largest seasonal thermal energy storage worldwide announced up to now. I'm going to take each demo site and I'm going to dive a bit deeper into each demo site, listing all the technological innovations that we have for each one. So starting with the one with 18,000 cubic meter in Germany, the in-campus or the Reno Estes. In here, we have several challenges, but starting from the beginning, what we have in here is that we have 3 abandoned mines or 3 abandoned basins, and we are going to reuse those abandoned basins and rehabilitate them to be active as seasonal thermal energy storage. By that, we are going to address the repurposing and reuse of legacy infrastructure as seasonal thermal energy storage. Those basically are connected structurally, and in the future, they are hydraulically also connected, and the goal later within the project to connect them thermally, and I'm coming back to this point later. Now, those three basins, they have a total volume of 18,000 cubic meter. That means it is split between them, but unequally. We have one basin with around 5,000 cubic meter, while the other with 9,000, roughly 9,000 cubic meter, and the rest goes for the basin that we have in the middle between the both of them. So Those three basins are going to be filled with water gravel as a storage medium, and the main idea behind using water gravel, with that we can increase the structural stability and mechanical stability of the basin itself or the entire seasonal thermal energy storage, leading to a significant reduction in the cover costs. Because if you look around, especially in the Danish experience, you will find out that the major part of the capex goes most of the time for the cover, and we would like to get rid of that one, and that's why we have decided also for the water gravel as a storage medium or as a filling material for the basin, the three basins, in order to reduce the cover aspects and the cover specific costs. Well, since we are using water gravel or solid media as a storage medium, this implies that we need to go for indirect charging and discharging methods, and here we focus to improve techno-economically, so to say, our charging and discharging methods by improving the design of the heat exchangers that are going to be embedded within the basins, within the filling material as well. And with techno, I mean that we are going to aim for increased surface area in order to increase the heat transfer rate, simultaneously economic considerations. By reducing the pressure losses, we are able to reduce the pumping costs as well. Then, since we have three basins that are going to be hydraulically and also thermally connected with each other, then we would like to develop a smart control algorithm, so to say. We call it a charging manager. There's also something that is going to be developed within Interstore's charging manager. Will take consideration of the different levels of the thermal energy that is incoming to the store, and will decide based on the temperature level and also the amount of the capacity to which of the three units can be charged, and then after that to which level within the unit can be charged this amount of thermal energy. This allows us and allows also the operators of those three basins to accommodate various sources of thermal energy and to accommodate all the thermal energy incoming from those various sources as well. Then, since we are looking at a seasonal application that might last over 3 months of storage period, then we would like also to invest some time into the insulation materials. And here we put some efforts as well into investigating the recycled and natural insulation materials like wood chips, sawdust, and coconut fibers. Could be also foam glass gravel later in a later stage. The main reason behind that one, they have a very good functionality from heat transfer perspective, and simultaneously they are natural materials or recycled materials, so they contribute significantly to the improved LCA and the low cost as well. And finally, if you see in here, you will recognize directly that we have a groundwater flow from the left-hand side of the picture to the right-hand side of the picture. And there's an interaction between the seasonal thermal energy storage and also the groundwater that might lead later to some drastic implications and impact on the groundwater quality as given by the legal frameworks, and also to increase the thermal losses from the seasonal thermal energy storage. So our solution, which is quite innovative in here, is by inserting here a planar geothermal trench on the downstream of the groundwater flow after the storage with a given distance, in order to absorb the thermal losses and to reduce the groundwater temperature due to the thermal losses under controlled conditions. So that was all about the first demo site. And for the second demo site, which will be in Finland, as I said, it has a total volume of 1 million cubic meter, and it is splitted equally into 3 caverns. So basically for this one, we are looking at cavern thermal energy storage, which is quite different compared to the other projects, and it's something more innovative. The main reason behind that one, with the caverns, we can achieve very high temperatures beyond 130 degrees Celsius. However, that makes also a challenge because we are going to use a pressurized water as a storage medium. Since we are using high pressure and high temperature, this gives you a lot of, or a set of challenges on the material improvements. So within the project also, there is several tasks focusing on the improvement of the sealing and the liners in order to prevent the leakage, and also to improve the construction materials in order to make them kind of withstanding the high pressure that can go up to a maximum of 10 bars. Then, since it is well allocated in the subsurface with around 40-meter depth, then we need also to consider one important aspect, which is the thermal, hydraulic, and mechanical that will be developed within a modeling approach in order to detect any fracture propagation into the ambient rock, or heat propagation, or any leakage propagation into the ambient rock. The main important outcome, or the main important advantage of this approach with cavern thermal energy storage, is that you can achieve a reduced land space footprint by around 90% according to our calculation. And with that, you can have a very well techno-economic and environmental seasonal thermal energy storage. Now, to achieve those two demo sites with their innovative goals and solutions, embedded solutions, so to say, Interstores follows a multi-dimensional improvement matrix, starting from the storage, which is the cornerstone of the Interstores, focusing more as a component, improving the efficiency, reducing the thermal losses via the geothermal trench, simultaneously putting some efforts into also the improvement of materials, improvement of the control strategy. This will help us later by securing a very smart integration and robust integration as well of the storage within the energy system in order to have a secured supply of energy, heat or cold, to the customers. And then after that, we are hitting the third dimension, which would be, in this case, the environment, because as we are using, for example, the recycled or natural insulation materials, we are improving the economy by having a circular economy, as we are reducing also the space demand and the space footprint. Then we are also having a very good impact also on the LCA perspective. Those three dimensions will help us also later to increase the uptake and accelerate this uptake of these solutions within Interstores for the market by showing that there is really very low risk on investments, very reduced capex, and also can be transferred, and they are scalable to any other site that we have or we can consider. So, well, basically that was all from my side, and I would be more than happy to answer your questions. And before jumping into that, actually, I would like to, I can see it here. Yeah, exactly. I would to convey my acknowledgements and thanks to all the partners and within the consortium of Interstores for contributing to this presentation. Thanks all.
Perfect, wonderful. Thanks, Abdul, also for your last presentations. We are a bit over time, but we're gonna cut a bit into the next part of the presentation, next part of the webinar. Introduction to the panel discussion we will have now with all the 4 speakers as panelists. In the meantime, there are still a couple of questions open in the Q&A box, so feel free to still ask questions and the speakers to answer these questions in the Q&A box. Beside this, I would like to introduce now a couple of aspects we pre-discussed in the renewable heating and cooling technology platform. What are there's a couple of challenges. Some of them has already been addressed in your talks. But I still would like to highlight some challenges we pre-discussed and engage with you a bit. What of these challenges you in your projects identified as the main challenges, and how you are addressing those challenges in the last 23 minutes of that webinar. So that has been the price of land, the geological conditions and urban constraints for areas for putting storages in, the options of dual land use, so using the surface area for other, like photovoltaic, for example, environmental constraints. I think after you talked also about groundwater temperatures, what are the impacts and challenges here? Another aspects or challenges related to market regulation, construction and material challenges, aspects related to monitoring and optimization of the storage and charging and discharging strategy. So these 8 aspects we pre-discussed a bit on within the renewable heating and cooling technology panel and horizontal working group on districts. So I would like to go now, ask each of you, starting with Wim, which of these challenges do you see as the most important or most difficult to, or the most impactful, and how your project, how a treasure is addressing these challenges, or which of these challenges is addressed by treasure? Wim, some minutes for you to answer. These short answers like to address all speakers.
It's hard to say which are the most important, because a number of aspects are very important. Not only the price of land, but also the availability of land is very important in making a system work. And the experience with previous projects showed that this can mean or can take a lot of time in the preparation of a project. So several years can pass until a project developer has obtained all lands that are needed for such a project. So there is one thing that we are trying to address by making developers aware of this challenge, and by showing examples of how the different projects, executed their project or their land acquisition. There are challenges in the construction and in the materials. So making sure that the construction has a long lifetime with minimal maintenance requirements, and the materials should also be equipped to withstand higher temperatures, because as you showed, the higher the temperature that you can store, the better the profitability is of the storage itself. Long time endurance of the materials is also important. So we are trying to address this by also monitoring very closely the different components of the system. And then, of course, the charging and discharging strategies very much rely on the configuration of the district heating system itself. So which sources are connected to the system, and these sources, in combination with the demand of the heat, determine what strategy will be the best for the given constellation. So these are one part of the aspects that we address also in Treasure.
Okay. Same question for Sylvia. 8 challenges. We identified which one do you see have the most are the largest challenges, and how are you addressing those challenges in the Users for Heat project?
Yeah, sure. Well, to start with, thank you for the questions, and I totally agree with what Wim was saying before. I think it's pretty much the same in different projects of this kind. Maybe what I can comment, it's of course, I think the main challenges in this field, it's what regards, let's say, let's put it in the framework of the environmental consideration, in the sense of regulations and permits, for example, which are very also location dependent. They might be rules and requirements which are completely different if you want to install the system, beside the specifics of the geological conditions, which maybe I was commenting in one of the questions in the chat. And for that, I think it's very much, I mean, there are different technologies that could be used for underground solutions, and depending on the, let's say, availability that you have from a geological perspective, then you can probably identify what is also the best solution for your specific case. But beside that, there are a number of rules and regulations which are, again, completely different from place to place. And then it becomes also very tricky from knowledge sharing and, examples and community building, in this sense of having common progress, let's say, in this sense. So I think this is a challenge that, I mean, the more the project, the better, and the more these regulations are addressed somehow, but at the same time, there should be also some kind of probably higher level effort in this direction. I also see another challenge in the sense of monitoring, let's say, and the whole operational part of these storages, which to start with are generally meant for seasonal applications, and they typically have rather long payback time or return on investment, as you were saying at the beginning. And this leads to, time before you actually see the benefits, both from the economical, but also from the purely energy, since, for example, when it comes to boreholes, for the first years, you actually have to heat up the ground, basically, and that's how it works. But then it's going to have effect afterwards. And for several different applications, this might be a big barrier in general, and some kind of constraint that needs to be addressed from maybe the industrials or people actually potentially investing into this. But of course, there are lots of opportunities in the sense of, for example, I do see a lot of potential for sector coupling, electrification, heat pumps integration, and all of these when it comes to the operational strategies around that, and not maybe just the use for seasonality itself, but also seeing that as an asset for making the whole network much more flexible overall. Yeah, I think this would be my main reflections upon these points.
Thanks for your statement. Same questions to Safa, although I would like to add, as you have the one presentation that is not using water or stones as the main energy carrier, but a chemical material. I like to add maybe environmental considerations could have a special role in your projects. How are you addressing these environmental considerations in your project? And the other challenges we discussed about. How do you address those things in your project?
Question to me, I guess.
Yeah, to Safa, yeah.
Yeah, I mean, most of the chemicals we use, and I think this thermochemical will be like the vermiculite, which is a natural, comes from the ground, and the calcium chloride that also comes from the ground as a mineral. So therefore, all the material is on the thermochemical side will be just natural materials. At the end of this useful life, you can always send it back to the earth, landfill sites. That's the thermochemical side. Thermochemical is easier. On the phase change material, if you use phase change material, latent heat aspect of it, again, most of the preferred phase change materials are hydrated salts. And again, the salts comes from naturally from mining earth and the water. The only exception to that, like the organic phase change material for latent heat, they could be like the paraffin waxes or whatever the name you call it, bio. The only way you can dispose of them is by burning, and you cannot send it back to the landfill. Yes, of course, there is basically, especially also on the harvesting of this material, the mining, there's some sort of environmental impact, as well as, of course, energy consumption. But I think you need to balance those two with the amount of CO2 savings from shifting the loads or utilizing solar energy or free energy. But at the moment is we are not necessarily going into the environmental study as part of our projects. Our projects is the prove the concept we can boost that data center, which is throughout the world, is everywhere, these data centers, and consume significant amount of energy, and they're wasting a lot of energy. So if you can recover that, instead of having like what you described, a 1 million cubic meter of space is not available everywhere in Europe. But in comparison, for 1 million, I just worked it out. If we use thermochemical, we only need 1,000. So ratio significant in terms of that. Also, excavate a 1 million cubic meter of earth to build a thermal storage versus 1,000 cubic meter, as it makes a lot of in terms of the capex aspect of it, economics. But yes, at the moment, as our study is not going to look into the environmental side of it, purely the practical side. Can it be done? Can it be, if you like, demonstrated? It can be done, because beyond the data centers, we have a lot of other waste heat in the cities, around the cities. So rather than trying to store everything in seasonal, which is very, very difficult because the size becomes so big, and size means also cost goes up, and it's sometimes very difficult to justify economically. And therefore, if we can find a way, utilize what we are wasting throughout the year and try to use that economically, that's the whole purpose of our Thunder. I hope this answers the question.
It does. Thanks for your answer. The same question to Abdul. You answered partly them already, but could you highlight again which of these challenges you see is the most urgent, and how are you addressing those in the project?
Yeah, so thanks, Rolf. Much has been said up to now about the challenge, so I'm not going to kind of invent a new challenge, but one of the things, or the challenge to me, it is the regulatory and legal frameworks. And this I often address also in my talks and the presentations. The main reason here, if you take, for example, the Austrian boundary conditions, the legal frameworks and regulatory frameworks as well, they state that the groundwater temperature must not exceed 25 degrees Celsius. The same goes also for Germany. They have a very restricted temperature limit. And now, where shall we measure this 25 or 20 degrees Celsius? Is it 5 meters from the side walls of the storage, or 10 meters, 20 meters? Now, if you take another case, which is Switzerland in this case, they tell you the temperature of the groundwater shall not change beyond 5 Kelvin 100 meter after the application or beyond the application. Here it is well specified. But when you look at the Austrian and German, for example, just focusing here in Middle Europe, as those two countries, it is not well stated. It is just a temperature that is legally binding, and that's it. And this actually implies a lot of challenges during construction. Why? Because in order to maintain this groundwater temperature, that means you would need very thick walls, you would need also some mitigation measures like cut-off walls, and next to that one you would need also very thick insulation materials or insulation layers. All of these will contribute significantly to the increase of the specific cost for seasonal thermal energy storage. So that was on one aspect. The other aspect, the way I see it as well, so as we are moving towards a sustainable future and circular economy, I always ask myself, even though, for example, if we take just a normal thermal energy, a seasonal thermal energy storage, which is an excavated pit, for example, an excavated site, what would happen after 30 years of service lifetime? What will happen to those pits? How can we use them? Are we going to rehabilitate them and put some extra money again and integrate them into the energy system, or something else? And this is the main thing that we are tackling also within Interstore project, is that, for example, let's say the cavern as a seasonal thermal energy storage is going to be into service for 30 to 50 years. Afterwards, it's going to be used as storage for another energy carrier that could be hydrogen, for example, or could be CO2 as well, as CCU and CCUS as well, part of a CCU-CCS carbon capture, utilization, and storage, or it could be also in the future something like compressed air energy storage. All of these shall be taken while we are doing the techno-economic and environmental analysis, because they have an impact on the entire portfolio, say. That was the second point. And the third point, I agree with what Wim said already. It is the space availability. The space availability, actually, it is one of the also major difficulties or challenges, I would say, because we don't have that much of space available currently, especially when you go to dense urban areas or dense urban cities. It's quite difficult to integrate them, and that's why we need to look for some innovative solutions. Such innovative solutions, we have many abandoned tunnels or many abandoned infrastructure. All of these can be used smartly and actively as seasonal thermal energy storage. I know they aren't water-based purely, but still, since they are limited, but they are there, we can also use them within a given temperature range. How to integrate them, there's another challenge.
Thanks, Abdul, for your statement. We have 7 minutes left of the webinar and about 28 days left for Christmas. So if you have a wish for Christmas on the EU regulations, Abdul, thanks for bringing up that topic on regulations. So if you have a wish on for Christmas for changing EU regulations to make seasonal energy storage more feasible, easier to implement, what would that be? What would be your 2 main wishes for the EU to change an existing regulation, an existing guideline, or on a national context? What would that be? Again, everybody has 1 minute to answer that question. Again, starting with Wim, what would be your wish for Christmas to change on a regulatory side to make seasonal storage more efficient?
It would be great if the EU would spend some money on making sure or organize a process in order to come to a common framework of standards and regulations all over Europe. So starting the process, making money available for people to work on this and make sure that this is in act within a few years. That would be a good Christmas wish.
Thanks, Wim. Same question to Sylvia. What is your wish for Christmas for changing the EU regulation or getting more money for doing things?
Yeah, well, I totally agree with Wim. So I will share his gift if he gets that. It would be great. And I would add maybe another point on, well, I think from maybe not the storage perspective, but more the district heating network perspective in that sense, having stronger long-term regulations when it comes to, for example, decarbonization policies, taxes around that, or any sort of additional costs related to CO2 emissions in that sector specifically, and the application of that throughout Europe in a sort of homogenized way, so that business plan could be done in a more reliable way, considering the long time of this implementation and processes. That would be great, I think.
Thanks for your point. Safa, you are based in UK, but I guess they also have regulations, and I guess you have an insight into EU regulations maybe as well, since you have a demo case in EU. What is your wish for Christmas on the regulatory side for the Commission, but maybe also on the national side in UK, whatever you have in mind to make your storage technology more feasible, more easy to integrate and demonstrate?
I think it is coming from the industrial side, rather academic. The less regulation and the less government, the better. And take the economic realities takes place, because by government stepping in and subsidizing various technologies is a very broad brush rather than individual. So all it happens basically squeeze the sector in terms of unrealistic subsidized technologies, whereby as soon as the subsidies goes, technology goes with it. So therefore really is the one way. Especially in the UK, our problem is our electricity prices, energy prices linked to the gas. So as soon as the gas price goes up, electricity price goes up, despite the fact most of the electricity comes from the wind and the solar. So therefore, there is a little bit mismatch, if you like. The vested interest creeps into these regulations, unfortunately dictated by politicians. Unfortunately, politicians are being dictated by the big business. And that is basically my only, approach would be the less regulation, less government, and take care of the economics and the reality of the commercial will be better. Yes, you need environmental regulations, otherwise you let them loose and they ruin the world. You know what happened. I can understand that aspect of it, but not the economic side of it, to dwell on the regulations, just to make sure they don't make a mess of everything. That's my experience.
Very good answer. Thanks for this one. Now, Abdul, last statement on your side. You already highlighted a bit on regulatory challenges, groundwater temperatures, but what it would be again your wish to for Christmas for changing regulations on the EU level? They might not be able to change these national regulations on groundwater temperatures.
Okay, so basically groundwater quality, it's a great interest. I have to say it like this, but it is an interest for the entire European Union. And that means we need a regular, so basically let's call it like this, environmental or European environmental regulation framework to have a predefined temperature level for the groundwater quality and where to measure it, how to measure it, and which application as well. Next to that one, and focusing more on the regulation aspects, the wish that I have actually for those who are submitting demonstration projects or demonstration of seasonal thermal energy storage to show a case or a case study that after 30 years of using this, let's mine as seasonal thermal energy storage, how it is going to be transformed and reused into another application. With that one, we can achieve really circular economy. The same goes for each single material and component used within the entire seasonal thermal energy storage. With that, you can ensure that both sustainable tomorrow and simultaneously also you have a circular economy. And the third thing, if I'm allowed to have 3 wishes, so that would be the subsidies, not only for the capex but also for the opex partially during the first years.
Yeah, very different approach than Safa had, but I would like not to comment on that since webinar is over. We are exactly at 3:30. My very own summary of the webinar is that I really like the idea of seasonal thermal energy storages. I see there's a lot of challenges we still have to overcome. Very interesting, very ambitious projects. And as I said in my very initial statement, the energy economic view, we have to decarbonize district heating. Fuels should be used, if at all, in winter. Renewable fuels for district heating should be used in winter. If we looking at realistic values, I hope they are getting more expensive. So these systems hopefully will be more feasible in the future, saving us burning biofuels, burning hydrogen to heat homes. That's my very personal final feedback on this webinar. There has been a lot of question and answers. Some are still open. There's a lot of stuff has been answered. As had been pointed out, the slides will be sent to the participants. There will be a recording available, I believe, in the Youth and Power YouTube channel. Yeah, thanks a lot for your participation. Up to 100 participants we had in the webinar, very good number. Yeah, I'd like to end the webinar now. Thanks to all speakers for presenting and engaging in the panel discussion. Looking forward for cooperate maybe with you or have similar webinars in the future, and also see how your projects are proceeding and what are the things will be developed and what successes we will see in the future. Thanks everybody. Have a nice evening, and thanks again to Youth and Power for organizing the webinar.
Thank you. Bye-bye.
Thank you all. Bye-bye.
Thank
Have
you
a nice
all.
evening.
Bye.
Bye-bye.
Bye-bye.